Hello folks, I'm Mr. Pinola, and today we're going to take a look at a distance versus time graph. You've done this before, so hopefully this should be some practice for you once again. Now, if you remember, a distance versus time graph has distance along the y-axis, it has time along the x-axis, and it shows us what's happening to an object. What's happening in this particular graph? Well, notice an object is starting at the origin, and then it is moving to a position, a distance of 6 meters. That took 2 seconds. That means that this object is moving at 3 meters per second. It's traveling 3 meters every second that goes by. Then the object is at rest for a little bit. It's staying at 6 meters. So it's not moving here in this middle part, and its speed is 0 meters per second. Then, during this last part, the object is moving back towards the origin. Now, it doesn't quite make it there. It goes from a position of 6 meters to a new position of 2 meters, but it is moving closer to the origin. And notice it has a negative slope. That means that it has a negative speed, which means you're heading just towards the origin. So, what do we know about this graph? Well, we know that it is moving at a fast, constant speed in the beginning. We know that it is at rest in the middle, moving at 0 meters per second. And then it is moving at a slower, constant speed back towards the origin, even though it doesn't quite make it all the way back. Now let's take a look at the graph again. If you've got a keen eye, you might notice that I have changed one thing about the graph. It's not a position or a distance versus time graph anymore. Instead, it's now a velocity versus time graph. That means that we're going to be looking at velocity, which is very similar to speed against time. No information about distance, but now we have information about velocity instead. You'll notice that I kept the exact same line on my graph. So you might be thinking that it's doing the same exact thing. You'd be wrong if that's the case. Let's take a look at what exactly is happening to the object in our velocity versus time graph, because now everything's different. Meaning every time you look at one of these graphs, you have to ask yourself, is it velocity versus time or is it distance versus time? So let's focus on the first part of our graph, which is this line that slopes upward from 0 to 2 seconds. Now, during this time, in the distance versus time graph, we said that it was showing an object that was moving at constant speed away from the origin. But now, this object is not moving at constant speed anymore. And that's because its speed, which is very closely tied to its velocity, is increasing. Notice it started at a speed of 0 meters per second. And after 2 seconds, it is at a speed or a velocity of 6 meters per second. It's gotten faster. It's gone from 0 meters per second all the way up to 6 meters per second. So now we know that during the first part of the graph, the object is speeding up. Let's see if we can use the 3-step method to figure out what the acceleration of the object is during that time. Now I'm going to do the 3-step method in this part of the board that I have over here. I'm going to do it vertically, but if you prefer to write it out horizontally, that's perfectly fine. Now, I know that the object in the first part of the graph, the part we're talking about right now, starts out at 0 meters per second. Well, that's the starting speed, which means that's the initial velocity of the object. Eventually, it gets up to 6 meters per second. So it was speeding up the whole time. Well, that means that our final velocity is equal to 6 meters per second. And also, it might be helpful to know how much time that took. Well, this part of the graph that we were talking about, it took 2 seconds. Finally, let's say what we're looking for. Remember, we wanted to find what was the acceleration of the object during this time. So, do you remember our formula for acceleration? I hope you do. It is that acceleration is equal to the final velocity minus the initial velocity, all divided by the time. And so in this problem, well, to find acceleration, as our third step would show, we just need to take the final velocity, 6 meters per second, subtract the initial velocity, 0 meters per second, and divide by the time of 2 seconds. If you do that on your calculator, 6 minus 0 is 6. 6 divided by 2 is 3. That means our answer is that the acceleration is 3 meters per second squared. But what does an acceleration of 3 meters per second squared mean? Well, let's go back to our graph. Notice that after 1 second, the object had increased its speed from 0 to 3 meters per second. Then, after another second passes, it goes from 3 to 6 meters per second. By saying 3 meters per second squared, really what we mean is that the speed increases by 3 meters per second for every second that the object is in motion. So, as we can tell from this value for our acceleration and what the graph is doing, the object is clearly speeding up. So if you see a line that slopes upwards like this on a velocity versus time graph, it does not show constant speed. Instead, it shows that you are speeding up. Now let's take a look at the second part of our graph, this flat line here. Well, on a position versus time graph, or on a distance versus time graph, that represented being at rest. You weren't moving. You were staying at the same distance during that whole time. But now, this does not mean rest. That's because during this whole time, this object is locked into a speed of 6 meters per second. If you're moving at 6 meters per second, you aren't at rest. You're just moving at a constant speed. Your speed isn't changing, so you're not accelerating, but you're certainly moving. Your speed would have to be 0 to be at rest. So a flat line on a velocity versus time graph means that you are moving at a constant speed, not that you are at rest. Now let's take a look at how we would use our 3-step method to calculate the acceleration of the object during this middle part. You might already know what the acceleration is here. Remember, when an object is moving at constant speed, it has no acceleration. It should come out to 0. Let's prove that. This object at 2 seconds was moving at 6 meters per second. So that means the initial speed or the initial velocity is 6 meters per second. Then the object was moving for 2 seconds and it stayed at 6 meters per second. So the final velocity is also 6 meters per second. Now, what about the time? Well, the time is not 4 seconds. The time is 2 seconds because the object was moving in this way from 2 to 4 seconds. So 2 seconds had passed. So now let's find the acceleration in meters per second squared once again. We will use our formula, A equals Vf minus Vi over T. And we're going to plug in our numbers. So A is equal to 6, which is the final velocity that it got up to, minus 6, which was the initial velocity that it started at, all divided by the time of 2 seconds. Well, 6 minus 6, that's 0. And 0 divided by 2 means that my acceleration is 0 meters per second squared. Hopefully you expected that. Remember, if something is not accelerating, that means its velocity is not changing. And this value tells us that the object's speed is changing by 0 meters per second every second. In other words, it's moving at constant speed, not changing how fast it's going, but it is moving. Now let's take a look at the last part of our graph, which is where the line is moving downwards. And this gets a little tricky. What's going on here? Well, the object is not moving back towards the origin. It's still moving further away. Most people think that the object has turned around and now it's going downhill. That's not true. The reason we know that is that the velocity is positive this whole time. If the velocity ever became negative, then that would mean that the object is heading back towards the origin. But since the velocity is still positive, this object is still moving further and further and further away from where it began. But what is happening to it? Well, notice the velocity is decreasing. At 4 seconds, it had a speed of 6 meters per second. But at 8 seconds, it had a speed of only 2 meters per second. It slowed down from 6 to 2 meters per second. That means that we have an object that is slowing down if the slope goes downwards. So a line like in the first part, sloping upwards, meant speeding up on a velocity versus time graph. Flat meant we were moving at constant speed and not accelerating. And sloping downwards clearly means that we are slowing down, which is still an acceleration because the velocity is still changing. Now let's wrap up our video by finding the acceleration during this last part. It's a little tricky. The initial, or the starting speed or velocity, is 6 meters per second. That's how fast the object was moving before it started slowing down. At the end of this motion, the object is traveling at 2 meters per second. So now it is much slower. So 2 meters per second is our final velocity. What's the time? Well, this whole motion went from 4 to 8 seconds. That represents 4 seconds worth of time. And lastly, we're looking for the acceleration once again. I would expect this acceleration to be negative because the object is slowing down, and a negative acceleration usually implies that you are slowing down or your velocity is decreasing. So we'll go to our equation. Acceleration equals final velocity minus initial velocity divided by time. And we'll plug in our numbers. Let's be careful. VF is 2 meters per second. VI is 6 meters per second. And the time is 4 seconds. 2 minus 6 is -4. And -4 divided by 4 is an acceleration of -1 meters per second squared. Notice we got the negative number we wanted. So let's take a look at our graph once again. As we wrap up, we can see that this object is changing its velocity by 1 meter per second every second. And it's slowing down or decreasing its velocity by that amount, and that's why our acceleration was negative. I hope you learned something today about velocity versus time graphs, which are a little bit different from distance versus time graphs that we've learned before. Remember, in a velocity versus time graph, a line that's sloping upwards like this does not mean constant speed. It meant constant speed in a distance versus time graph, but now this is showing speeding up. The flat part here, well, on a distance versus time graph, that meant being at rest. But now it means moving at constant speed on a velocity versus time graph. And finally, during this last part, on a distance versus time graph, this would mean that you are just coming back towards the origin. But now on a velocity versus time graph, it means slowing down. Remember, when you look at a graph, the first thing that you should look for is to see whether it is a velocity versus time graph or a distance versus time graph. They are very different and they tell very different stories. So make sure the first thing you do is you look at which type of graph you have. Lastly, I want to point one thing out that we really didn't talk a lot about when doing our analysis of that velocity time graph. Do you notice how the line at the beginning is really steep and the line at the end is not as steep? Now, in a distance versus time graph, a steep line meant a fast speed. But in this case, a steep line does not mean a fast speed. Instead, if you see a steep line like this one on a velocity versus time graph, it means that your speed is changing very quickly. That would mean that your acceleration is very big. So, on a velocity versus time graph, the slope of the line tells you what the acceleration is. And remember, acceleration is a measurement of how quickly you change your velocity. So if you see a line that is very steep, whether it's pointed up or down, that would tell you that the object is changing its speed, whether it's speeding up or slowing down, really quickly. But if the line is not very steep, it still means it's changing its speed. That's just not happening quite as quickly. And that means that the object would have a lower acceleration. Thanks for watching.